So let's look at a simple application of k-means just to get more of a feel for it. So for example, if we wanted to do lossy data compression, how would we use k-means to do that? So this isn't necessarily what's done in the most state-of-the-art techniques, but let's take a look at what we would get with this. So here's our original image. It's 1024 by 1024 grayscale image. So you can think of this as a matrix that's 1024 by 1024. And each value in this matrix is 1 to a number between 0 and 255. Now what we do with this is we chop this up into 2 by 2 patches. So we take it and we chop it up into two columns of width 2 and rows of width 2. And then we treat each 2 by 2 patch as a 4-dimensional vector. So each 2 by 2 patch now becomes a data point in R4. And we have a bunch of these points, and that's what we're going to do k-means on. So we learn k-means on these points in R4. For example, we learn 200 clusters. We then take each 2 by 2 patch and we replace it in the image with the centroid that it was assigned to. So in the original image, we have these 4-dimensional vectors that are vectorized versions of 2 by 2 patches that can take almost any value. There are many different unique values. Now if we look at this image and we look at any 2 by 2 patch, there are only 200 unique values that those patches can take, corresponding to the 200 centroids that we learned, where we replace the patch with the centroid that it was assigned to as indicated by its corresponding value of C. So what we've done here is reduce this from about 1 megabyte to 239 kilobytes. If we want to compress it more, maybe we take all of these 4-dimensional vectors we extract and learn 4 clusters, and then replace those clusters with those points with their centroids, and we get something like this. So we've degraded the quality, but we've compressed it from 1 megabyte to 62 kilobytes. And again, if we looked at any 2 by 2 patch in here, now it can only take 1 of 4 unique values. All right, so lastly, I want to very quickly discuss an extension of k-means. K-means is called k-means because of the squared Euclidean distance measure that we're trying to minimize in the objective. But what if we want to use a different distance measure? So that leads to something called k-medioids. And so let's look at the algorithm for k-medioids here. So here we again input data x1 through xn. Now it does not have to be in RD, it can be anything. And we define a distance measure between any data point x and a centroid mu. Previously this was the squared Euclidean distance for k-means. Now it can be anything. We take out in the objective function for k-means the squared Euclidean distance, and we replace it with this distance measure. And now, how do we optimize this thing? So if we can follow exactly the same steps previously, where we iterate the following 2 steps, where first, in an iteration, we want to update CI, and so we set CI to be equal to the index of the cluster that the point xi is closest to, according to this distance measure. So that's the key difference. We now use this distance measure to assign each data point to its nearest cluster, where nearness is measured by this measure. After updating each cluster assignment, we then update each cluster centroid, where now we want to minimize over mu, over the centroid, the sum of these distances over each data point that was assigned to the cluster we're updating. So if we're updating the kth cluster, then we update the sum of the distances using only the data that was assigned to the kth cluster according to our update of C. So this thing for the squared Euclidean distance was analytic. We could take its derivative set it to 0, and find the optimal setting for mu using an equation. Now, according to what distance measure we use, perhaps we need to run an iterative algorithm to minimize this thing in mu. So in that case, we would have nested iterative algorithms. In each iteration of the k-medioids algorithm, we would have to call an iterative algorithm to update each centroid mu k. So let's, for example, what would we use? We saw already that with k-means, we simply define this thing to be the squared Euclidean distance. However, if we wanted to make our algorithm more robust to outliers, so we've seen in some previous slides how if we have an outlier in our data set and we calculate the mean, that outlier can drag the centroid out quite a bit. If we want to define an algorithm that's going to be robust to these types of outliers, we might want to use the L1 distance. So this, remember with the L1 regularization, the lasso for linear regression, we saw how this led to sparsity. So it also can be used here to make this distance measure more robust so that outliers can't drag these centroids out towards them as much. Also, if our data is not in RD, so this would be another example where we're working in RD. If our data is something more complex, we could define a more complex distance measure. For example, if the data is a histogram of counts of the number of times a word appears in a document, then maybe we want to define a more appropriate distance measure that would take into account the support of the data set.